Far beneath the quiet surface of Lake Huron, there is a world almost no one ever sees. Not beneath its shores, not beneath its harbors, but beneath the water itself. More than 500 meters below the lake's cold blue floor, enormous white corridors stretch outward in every direction, reaching farther than any single light can follow. The walls glitter softly in the darkness. The air is still and cool. The silence is so complete that the only sound is the faint hum of machinery somewhere far in the distance, a gentle reminder that human hands built this place and human hands work here still. This is the Goderich Mine, and it is one of the largest operating salt mines on Earth. Most people who have ever driven along the shores of Lake Huron have no idea it exists. From the surface, the town of Goderich, Ontario, looks exactly as a quiet Canadian lake town should look, church spires rising against a grey autumn sky, fishing boats resting in the harbour, old brick buildings lining a town square that has barely changed in 100 years. The lake stretches westward without any hint of what lies beneath it. The water is calm, the horizon is clean, everything appears exactly as it is, except that it isn't, because beneath those peaceful waters, beneath the soft lake sediment and the ancient bedrock and the accumulated weight of geological time itself, there is an underground city made entirely of salt, a place where rooms the size of concert halls stand in perfect silence, where pillars of crystallized ancient sea rise from the floor to the ceiling, where every surface reflects light with a faint milky luminescence that makes the air feel almost alive. And somewhere in this underground world, the walls themselves hold a memory of something that existed long before the lake, long before the land, long before anything that currently lives and breathes on the surface of North America. The walls of this mine are the remains of an ocean that vanished more than 400 million years ago. How did an ancient sea become solid rock beneath a great lake? Why does one of the world's largest underground salt cathedrals lie directly beneath Lake Huron, a lake that most people associate not with ancient geology, but with fishing boats and summer holidays? And what does this quiet underground world reveal about the deep history of an entire continent? Those questions are worth sitting with for a moment, because the answers are not simple and they are not quick, and perhaps that is part of what makes this place so remarkable. The Goderich Mine is not a place that reveals itself easily. It requires patience, it requires descent, and it rewards that patience in ways that few places on Earth can match. If you're enjoying tonight's quiet journey beneath Lake Huron, we'd love to have you with us. A quick like, subscribing to History Sleepy Time, and leaving a comment telling us where you're watching from helps us continue exploring the hidden places of our world. Now, let's continue our descent. The town of Goderich sits at the point where the Maitland River meets Lake Huron, on the eastern shore of the lake in southwestern Ontario. It was founded in 1827, laid out in an octagonal plan that gives it an unusual, almost mathematical elegance. 8 streets radiating outward from a central courthouse square like spokes from a quiet wheel. The town has always been small by the standards of modern cities, its population hovering somewhere around 7,000 or 8,000 people across its long history. But what Goderich has always possessed, that most towns cannot claim is something invisible, a remarkable geological inheritance hidden directly beneath its feet. The region sits atop one of the most extraordinary deposits of rock salt in North America. The deposit extends far beyond the town limits, stretching outward beneath the surrounding farmland, beneath the lake shore, and eventually, remarkably, beneath the open waters of Lake Huron itself. The salt lies in layers, compressed and preserved within ancient sedimentary rock, at depths that range from several hundred to more than 1,000 meters below the surface. It is not a small deposit. Geologists estimate it contains enough recoverable salt to supply the entire world's needs for centuries. But for most of the town's early history, that underground world was invisible. It was suspected, in a vague way. Settlers and early surveyors noticed that springs in the area carried salty water, and that was unusual enough to attract attention. But the full scale of what lay beneath the ground was far beyond what anyone could have imagined in the early decades of the 19th century. The mine as it exists today, enormous, structured, intricate, reaching beneath the floor of the lake, is the product of more than a century and a half of gradual discovery, careful engineering, and the quiet accumulation of geological understanding. To visit the mine today is to enter a different kind of world entirely. The journey begins at the surface, at a cluster of industrial buildings near the lake shore that serve as the mine's surface infrastructure. The elevator shaft rises above the entrance like a modest industrial tower. Nothing about it prepares you for what waits below. Visitors and workers alike enter the cage, a steel elevator platform that will carry them downward through several hundred meters of solid rock, moving slowly enough that the transition feels almost ceremonial. The light from above fades. The walls of the shaft move past, rough grey limestone, then red shale, then older and older rock as the descent continues. Then something changes. The rock around the shaft becomes white. Not grey-white or cream, but a clean, bright, crystalline white that seems almost to generate its own light. And when the elevator finally stops, when the cage opens into the underground world, the first impression is of space. Enormous, unexpected space. The ceiling rises high above. The floor stretches outward in every direction. The walls, smooth and pale and faintly glistening, recede into shadows that the eye cannot entirely follow. The air is cool, not cold, not uncomfortable, but noticeably cooler than the surface, with a faint mineral dryness that settles in the back of the throat. There is almost no humidity here. The salt absorbs what little moisture the air brings down from above, leaving everything in a state of perfect, preserved stillness. Underground, the temperature barely changes with the seasons. Summer and winter above ground mean very little in the world below. The mine maintains its own quiet, steady climate, independent of whatever the sky is doing 500 meters overhead. The tunnels extend outward from the main shaft in a branching network that, taken together, spans dozens of kilometers. There are roads here, actual paved roads wide enough for heavy machinery, carved directly through the salt rock. There are intersections and junctions. There are designated working areas and older sections, some still active and some gradually falling quiet as extraction moves to different zones. Walking through the main corridors is a little like walking through the streets of a very silent, very pale city. One where the buildings are made not of brick or concrete, but of crystallized ancient ocean. And it is that ancient ocean, the one that built these walls, grain by grain, over countless millions of years, that deserves to be understood before anything else. Because without that ocean, none of this exists. Without that ocean, there is no mine, no salt, no corridors, no cathedral of white stone beneath Lake Huron. The entire story begins not here, not in Ontario, not even in the recognizable geography of North America. It begins somewhere that no longer exists in any form we would recognize. A warm, shallow, sunlit sea that once covered much of what is now the eastern half of a continent. To understand the salt beneath Lake Huron, it helps to let go of the familiar landscape entirely. Forget the lake, forget the forest and the farmland and the gentle hills of southwestern Ontario. Forget the maple trees and the grey Canadian sky. Set aside everything that makes this part of the world look the way it looks today, because 400 million years ago, during the geological period scientists call the Devonian, none of it existed in any form that would be recognizable. The land itself was in a different position. The tectonic plates that carry the continents were arranged differently than they are today, having spent hundreds of millions of years drifting, colliding, and rearranging the surface of the Earth in ways that are still being mapped and understood. What would eventually become North America sat closer to the equator. The region now occupied by the Great Lakes, by Lake Huron, Lake Erie, Lake Superior, the whole familiar chain lay in a warm, low-latitude zone, somewhere in the southern hemisphere, bathed in tropical sunlight. And across much of this ancient continent, where dry land now stretches from horizon to horizon, there was water. Shallow, warm, sunlit saltwater, a vast inland sea that geologists refer to broadly as the Devonian Epiric Sea, spreading across the interior of the continent in a shallow, slowly shifting body of water that would look nothing like an ocean to modern eyes. It was rarely deep. In many places, it may have been only a few dozen meters from surface to floor. Its edges were irregular and shifting, advancing and retreating as the land tilted slightly under geological pressures that operated over millions of years. But in the region that would one day become southwestern Ontario, this sea was persistent. It stayed. It deposited its sediments, its muds, its limestones, its organic materials, over and over again, layer after layer, building up the rock that would eventually define this landscape. The Devonian period itself lasted roughly 60 million years, from approximately 419 million years ago to 359 million years ago. It was a remarkable chapter in Earth's history, sometimes called the Age of Fishes. Because the seas of this period hosted an explosion of fish diversity that had never been seen before, with armored fish and early sharks and strange lobe-finned creatures, whose descendants would eventually leave the water entirely and begin the long evolutionary experiment of land-based vertebrate life. The land surrounding these shallow seas was also beginning to change. The first forests were appearing. Early trees were putting down roots in the Devonian soil, their root systems slowly breaking rock and contributing to the development of something that had never existed before in Earth's history, genuine soil. The world was greening slowly in a way that would eventually transform the planet's atmosphere and climate. But in the interior of the continent, where the inland sea spread quietly across the ancient lowlands, the story was different. Here the climate was warm, genuinely tropical, and the sea was shallow enough that sunlight reached the bottom in most places. Corals built reefs along its margins. Strange creatures called crinoids swayed in the gentle currents, anchoring themselves to the seafloor and filtering food from the water with feathery arms. Brachiopods, small, clam-like creatures with hinged shells, were everywhere, so abundant in some zones that their shells accumulated in thick layers on the bottom, eventually becoming the limestone and dolostone that still forms the bedrock of much of the Great Lakes region today. For much of the Devonian, this sea existed in a relatively open connection with the larger world ocean, a broad, shallow communication that allowed water to flow in and refresh the basin. But periodically, geological forces shifted. The sea gradually lost its open connection to the ocean. The margins of the ancient continental basin rose slightly, or sea levels dropped, or the geometry of the land changed in ways that reduced the flow of new ocean water into the interior basin. And when that happened, when the inland sea began to lose its connection to the wider ocean, something quite specific began to occur. The sea began to evaporate. This is not an unusual geological process. It happens today in places like the Persian Gulf or in coastal salt flats around the world, wherever seawater is concentrated by evaporation in a closed or semi-closed basin. The physics are straightforward enough. Seawater contains dissolved salts, primarily sodium chloride, the same compound we know as table salt, but also calcium sulfate, magnesium compounds, and a range of other minerals. When seawater evaporates, the water itself disappears into the atmosphere as vapor, but the dissolved minerals cannot evaporate. They remain behind. And as the water level drops, the concentration of dissolved minerals in the remaining water increases. Eventually, when the concentration reaches a certain threshold, the minerals begin to crystallize out of solution and settle onto the seafloor. Geologists call these deposits evaporites, a clear and simple name for a remarkable class of rock. They form only under specific conditions, requiring warm temperatures, high evaporation rates, restricted water circulation, and a sufficient source of mineral-rich water. The Devonian Inland Sea over what is now southwestern Ontario met all of these conditions, not once, but repeatedly over millions of years. The sea would partially evaporate, depositing layers of salt and other minerals. Then conditions would shift, and new seawater would enter the basin, diluting the remaining brine and depositing limestone over the evaporite layers. Then the cycle would repeat. Layer upon layer was built up over geological time: limestone, then salt, then more limestone, then more salt, a stratigraphic record of a sea breathing in and out over millions of years. The salt layers that resulted from this process are sometimes called the Salina Group by geologists studying this region, a series of evaporite deposits of Silurian and Devonian age that underlie much of the Michigan and Appalachian basins. The Goderich deposit is part of this larger geological story, sitting within a basin that extends beneath Lake Huron, Lake Erie, and into the American states to the south. The salt is not unique to one location. It is part of a vast underground salt province, one of the largest in North America, that formed when an ancient sea slowly gave itself over to the sun. At its thickest, in the region beneath Goderich, the salt deposit is several hundred meters deep. That is not a thin seam or a modest accumulation. It is an immense geological formation, the crystallized remnant of seawater that fell out of solution over a period of millions of years, preserved beneath younger rock and eventually beneath a lake that would not exist for another 400 million years. Every crystal in every wall of the Goderich Mine is in a very real sense a piece of that ancient sea, a fragment of water that evaporated long before the first forests had finished spreading across the land. Long before the first fish had left the water to breathe air, long before any creature capable of wondering about such things had begun to exist anywhere on Earth. It is worth pausing with that thought for a moment. The salt that miners cut from the walls of this mine today was deposited when life on land was still something new and experimental. When this salt was forming, the creatures living in the sea above it would have been entirely unrecognizable to modern eyes. The world was different in almost every way: the continents, the climate, the atmosphere, the biology. And yet the salt remained. Through everything that followed, through hundreds of millions of years of geological change, through the formation and erosion of mountain ranges, through multiple ice ages, through the appearance and disappearance of countless species, the salt simply stayed buried and patient and preserved, waiting beneath the accumulating weight of everything that came after. But the sea's disappearance was only the beginning of the salt's long journey through time. Once deposited on the ancient seafloor, the evaporite layers faced a new set of geological forces, ones that would slowly transform them from a scattered accumulation of crystals into the dense, compressed, remarkably stable rock that now forms the walls of an underground world. When the Devonian Sea finally withdrew for the last time, either retreating through a restored connection to the wider ocean or simply evaporating away in a final, permanent cycle, it left behind a landscape that was flat, mineral-rich, and gradually drying under the ancient sun. The evaporite layers that had accumulated on its floor now lay exposed or buried beneath thin sediments, waiting for the next chapter of their geological history. That chapter would be written slowly, very slowly. The continents continued to drift. Mountains rose in what is now the eastern part of North America, pushed upward by the collision of ancient tectonic plates. A geological event of enormous scale that geologists call the Acadian orogeny, a mountain-building episode that created peaks comparable in height to the modern Himalayas. Stretching along the eastern edge of the continent, rivers poured off those mountains and spread sediment across the interior lowlands. Layer after layer of sediment accumulated: sand, silt, clay, organic material, gradually burying the ancient salt beds beneath an ever-thickening blanket of younger rock. Hundreds of meters of sediment eventually compressed under their own weight into new layers of stone, This burial process is important to understand because it is what preserved the salt. Left at the surface, rock salt would not survive for long. It is soluble. Rainwater would dissolve it, rivers would carry it away, and within a geologically brief period, it would be gone. But buried beneath hundreds of meters of impermeable rock, sealed away from the groundwater and surface drainage systems that would otherwise dissolve it, the salt was protected. The overlying rock acted as a lid, trapping the salt in a closed geological vault where it could neither escape nor be reached by dissolving water. Over millions of years, as the weight of overlying rock increased, the salt changed in character. Salt behaves differently under pressure from the way most rock does. Limestone and sandstone and shale are relatively brittle. They crack under stress, fracturing along planes and breaking into blocks. Salt, by contrast, behaves more plastically under sufficient pressure and temperature. It flows. Not quickly, not in any way that could be observed over a human lifetime, but over geological time. Salt can migrate and redistribute itself, filling spaces, healing fractures, and maintaining an internal coherence that makes it remarkably stable as a construction material for underground spaces. This property, the plastic behavior of rock salt under pressure, is one of the reasons that the underground chambers of the Goderich Mine can be maintained at such impressive scales without the kind of elaborate support systems that other underground excavations require. The salt is self-healing to a degree. Small cracks and fractures close gradually under the pressure of the surrounding rock. The material has a memory of its own, a tendency to return toward equilibrium that makes it an unusual and in many ways forgiving material to work within. The crystal structure of rock salt also contributes to its visual character, the quality that gives the underground world its faint, diffuse luminescence. Halite, which is the mineral name for sodium chloride in its crystalline form, forms cubic crystals that interact with light in a distinctive way. Individual crystals scatter and reflect light in multiple directions, so that a lamp or headlamp directed at a salt wall does not produce a harsh point of reflected brightness, but instead fills the entire surface with a soft, distributed glow. The effect in a large underground chamber where the ceiling and walls and pillars are all formed from this same white crystalline material is one of gentle illumination, as though the room itself were generating a quiet, steady light from within. It is this quality, perhaps more than anything else, that causes people who have descended into the mine to use the word cathedral. The chambers are large enough and the light behaves in a way unusual enough that the underground world genuinely produces a feeling of architectural grandeur, not the grandeur of something designed for that effect, but the deeper and stranger grandeur of something that arrived at this appearance through entirely different means, through geological processes indifferent to aesthetics, producing beauty as an unintended consequence of physics and chemistry and time. Meanwhile, above the buried salt, the geological history of North America continued to unfold across vast stretches of time. The great mountain ranges of the East were slowly eroded down by rain and wind and the patient work of rivers. The interior of the continent was repeatedly flooded by shallow seas during different geological periods, each one adding new sedimentary layers above the ancient Devonian salt. Hundreds of millions of years passed. The continents continued their slow rearrangement. Life on land evolved from its first experimental beginnings into the extraordinary diversity of the Mesozoic, the time of dinosaurs, of early flowering plants, of birds beginning to diverge from their theropod ancestors. The geological record above the salt grew richer and more complex with every passing era. And then, in the relatively recent geological past, beginning roughly 2.5 million years ago, the climate of the Northern Hemisphere began to shift in ways that would have dramatic consequences for the Great Lakes region. Ice ages came and went, each one sending enormous glaciers southward across the continent, scraping and reshaping the surface of the land above the ancient salt. The glaciers carved the basins that would eventually become the Great Lakes. They deposited the moraines and till and outwash materials that give the landscape of southwestern Ontario its gentle, rolling character. When the most recent glaciation finally retreated, roughly 10 to 12,000 years ago, the landscape of the Great Lakes region began to take on something approaching its modern form. Lake Huron filled its basin with glacial meltwater. Rivers established their courses across the newly exposed land. The climate warmed, forests spread northward. And eventually, people arrived, moving across a landscape still recovering from the glacial period, finding rivers full of fish and forests full of game, and a lake so vast that its far shore was invisible on calm days. None of those first people could have known what lay beneath the ground. But the salt that had formed beneath a tropical sea 400 million years earlier was still there, still patient, still preserved beneath its blanket of younger rock. Now additionally concealed beneath the floor of a lake that had not existed until geological yesterday. The underground world was already ancient beyond any human measure before the first human footprint was made anywhere in the Great Lakes region. It would remain hidden for a very long time, but not, ultimately, forever. Salt has a way of making itself known. It announces its presence through the water that travels through the rock above it, water that, given the right geological conditions, picks up enough dissolved salt on its journey to the surface to carry a detectable taste long after it has left the evaporite layers far below. In the region around Goderich, this was exactly what happened. Springs and wells in the area carried water with a distinctly saline character, not potable in the way that fresh groundwater is, but not immediately dangerous either. And to people who understood the value of salt, that brackish water was a signal, an indication that somewhere beneath the surface, something more substantial was waiting. How those early signals were eventually followed, how curiosity became investigation. And investigation became the extraordinary underground world that exists today, is a story that belongs as much to the 19th century and to the practical ambitions of settlers and entrepreneurs as it does to the ancient geology that made any of it possible. But before arriving in that more recent chapter of the story, it is worth sitting for another moment in the geological depth of what this place represents. The salt in the walls of the Goderich Mine is not simply a mineral resource. It is a record, a physical archive of conditions on Earth that no longer exist anywhere on the planet. The ancient sea that produced it is gone. The world that surrounded that sea, the continents in their Devonian positions, the tropical climate, the strange Devonian biology, is gone entirely, replaced by 400 million years of subsequent history. Yet the salt remains. Compressed, preserved, crystalline, and patient beneath Lake Huron, it holds within its structure a chemical memory of water that has not existed as a sea in longer than the human mind can comfortably comprehend. There is something quietly extraordinary about that. About the fact that the walls of a working mine contain, encoded in their crystal lattice, the chemistry of an ocean that has not touched the surface of the earth in 400 million years. That is the nature of deep geological time. It does not announce itself. It does not demand attention. It simply persists beneath the lakes, beneath the soil, beneath the ordinary surface of a world that tends to be too busy with its present moment to notice the immensity of everything that came before. The discovery that something remarkable lay beneath the ground near Goderich came slowly, and it came from people who were not initially looking for geological history. They were looking for something far more practical. Something that, in the middle of the 19th century, was more valuable than almost any other commodity in the region. They were looking for salt. In the middle of the 19th century, salt was not a seasoning. It was a necessity. Before refrigeration, before canning, before any of the preservation technologies that modern life takes entirely for granted, salt was the primary means by which food could be kept through a winter, transporting across long distances, or stored against the uncertainty of a bad harvest. Salted fish, salted pork, salted butter, these were not culinary preferences but survival strategies practiced by communities across the entire settled world. The demand for salt was constant, urgent, and often difficult to meet. In many parts of North America, salt had to be imported at considerable expense from distant coastal operations or from European sources, and its price reflected that difficulty. Communities that could produce their own salt had an enormous practical advantage over those that could not. It was within this context, not geological curiosity, but economic necessity, that the first serious attention was directed toward the salty springs of the Goderich area. The Huron Tract, as the region was formerly known in the early decades of the 19th century, had been opened to European settlement through the efforts of the Canada Company, a land development corporation that had purchased an enormous grant of Upper Canadian territory from the colonial government in 1826. John Galt, a Scottish novelist turned colonial administrator, was among the founders of the Canada Company and played a central role in establishing Goderich as the principal town of the Huron Tract. The octagonal street plan that still defines Goderich's town centre was part of Galt's vision, a deliberate attempt to create not merely a functional settlement, but an elegant one, a town that would attract the kind of prosperous, educated settlers the Canada Company hoped to recruit. What the Canada Company and its settlers found when they arrived was a landscape of considerable beauty and reasonable agricultural potential, rolling land, mixed forests, a fine natural harbour where the Maitland River met the lake. but they also found those anomalous saline springs. Early settlers reported that certain wells and springs in the area produced water with a noticeably brackish taste. In some locations, the water was salty enough to suggest that something more than trace mineral content was responsible. The Canada Company began investigating these springs in the 1820s and 1830s, sinking test wells in an attempt to understand what lay below. The results were promising. Brine concentrated salt water was encountered at relatively shallow depths in several locations, and its mineral content suggested a substantial deposit somewhere further below. The company began producing salt by the simplest available method, pumping brine to the surface and evaporating it in large metal pans over wood fires. A technique that had been used to produce salt from natural brines for centuries and required no understanding of what lay in the deep rock below. This early brine production was modest. It supplied local needs and contributed to the regional economy, but it was limited by the concentration of the brine and the considerable cost of the firewood required to evaporate it. The quantities produced were useful, but not transformative. The full scale of what lay beneath the surface was not yet apparent to anyone working in the region. The real transformation came through drilling, specifically through the deep drilling technology that began to be applied across North America in the second half of the 19th century, originally developed in the search for oil following the landmark discoveries in Pennsylvania and Ontario in the 1850s and 1860s. Drill rigs could reach depths that earlier hand-dug or driven wells could never approach, and as drilling technology improved through the 1860s and 1870s, operators in the Goderich area began pushing test holes deeper than had previously been attempted. What those deeper wells revealed was a deposit of a different order entirely. At depths of several hundred feet, the drill bits were no longer passing through brine-saturated rock. They were encountering solid salt, not the trace mineral content of groundwater, but actual seams of dense, crystalline rock salt, meters thick, extending in every direction as far as the limited diagnostic tools of the era could determine. The brine at the surface had been a distant reflection of something far more substantial below. Beneath the agricultural land of Huron County, beneath the limestone and the shale and the various sedimentary layers that formed the local bedrock, there was an enormous salt formation, larger than anyone had guessed, richer than the most optimistic assessment had suggested. The commercial implications were immediately understood. Rock salt could be mined directly, requiring no evaporation and no fuel, only the excavation of the solid material and its transport to the surface. The deposit was deep, but depth was becoming a manageable engineering problem as mining technology advanced through the latter half of the 19th century. The question was not whether the deposit could be mined, but how and who would undertake the considerable investment required to do it. Various interests looked at the Goderich deposit across the 1860s and 1870s, and commercial salt production from the region's brine operations continued to grow. By the 1880s, Goderich had established itself as one of the most important salt-producing communities in Canada, with multiple brine wells and evaporation works operating in and around the town. Salt was shipped across Lake Huron and distributed through the Great Lakes network, reaching markets across Ontario and into the American Midwest. The town's identity became inseparably connected to salt, an identity that persists to this day. The transition from brine production to deep rock salt mining took longer, requiring both technological confidence and capital investment of a scale that took time to assemble. But by the early decades of the 20th century, the first serious rock salt mining operations were underway in the Goderich area. Shafts were sunk into the deep deposit, underground workings were begun, and gradually, over the course of many decades, what had started as a collection of brine wells producing modest quantities of evaporated salt became one of the largest underground mining operations in North America. The mine that exists today, operated by Compass Minerals, one of the largest salt producers in North America, is the product of more than a century of that gradual development. Its underground workings now extend beneath the lake itself, following the salt deposit outward from the original shaft location near the lakeshore. The scale of the modern operation is difficult to visualize from the surface. The underground road network runs for dozens of kilometers. The rooms and pillars of the extraction area cover a footprint that, if laid out on the surface, would encompass the entire town above it several times over. But the true scale of the mine is not measured in road lengths or surface area alone. It is measured in time, in the layered accumulation of decisions and engineering and labor and geological understanding that produced, over more than a century of work, one of the most remarkable underground landscapes in North America. There is something worth pausing over in this transition, from the saline springs noticed by early settlers, to the test wells of the Canada Company, to the deep drilling that revealed solid rock salt, to the mining operations that eventually produced the underground world that exists today. It is a story of gradual discovery, of knowledge accumulating through small steps across many generations. No single person saw the complete picture at once. No single moment of revelation explains everything. Instead, understanding arrived in pieces, a salty spring here, a promising well there, a drill bit returning salt cores from unexpected depth, a geological report connecting the local deposit to a broader regional structure. This is usually how geological knowledge is built. Not through dramatic discovery, but through patient accumulation. And it is a fitting parallel to the geological process that created the deposit in the first place. Also a matter of patient accumulation, of one thing added to another over stretches of time too vast for any individual to fully inhabit. The people who first descended into the solid rock salt beneath Goderich were not explorers in any romantic sense. They were miners, engineers, and workers with practical tasks to accomplish and practical dangers to manage. But they were also, whether they thought about it in these terms or not, the first human beings to enter a world that had been sealed away since, before the first forests grew on land. They were moving through geological history in a way that no map or textbook could fully convey, surrounded by walls that were older than any creature currently living on the surface of the earth. That quiet fact that the underground world of the Goderich Mine is older than everything visible above it has not lost its power across the many generations of miners who have worked there. It is not something that requires a geological education to feel. It is something the walls communicate simply by being what they are: massive, white, ancient, and still. Building a mine is not simply a matter of digging. It is a matter of designing a world. An underground mine, particularly one that reaches the scale of the Goderich operation, requires a level of engineering forethought that is not always obvious from the surface. Every decision made about the shape of a tunnel, the spacing of support pillars, the routing of a ventilation shaft, or the angle of a ramp has consequences that extend decades into the future, because the underground world, once built, is extraordinarily difficult to rebuild. The rock that has been removed is gone. The spaces that have been created will remain. The patterns of excavation become the permanent architecture of the underground landscape, and they must be designed with the long-term stability and safety of the entire structure in mind from the very beginning. The Goderich Mine was not built all at once. It was developed incrementally over the course of many decades as the understanding of the deposit grew, as engineering methods improved, and as demand for salt required the expansion of production into new areas of the underground formation. But through all of that incremental development, certain fundamental engineering decisions shaped the character of the mine in ways that are still visible and still relevant today. The most fundamental of those decisions was the choice of mining method. In an underground salt mine, where the goal is to extract as much of the material as possible while maintaining the structural integrity of the spaces that remain, engineers face a particular challenge. Remove too little, and the operation is inefficient. Remove too much, and the underground structure loses the support it needs to remain stable. The solution, developed and refined over many generations of underground mining practice, is an approach called room and pillar mining, a method elegant in its simplicity and remarkably effective across a wide range of geological conditions. In room and pillar mining, the salt is extracted in a pattern that leaves behind regularly spaced columns of unmined material, the pillars, to support the roof of the excavated area. Between the pillars, the extracted areas become the rooms, open spaces that can grow quite large while remaining structurally sound as long as the pillars are correctly proportioned to the depth and the mechanical properties of the surrounding rock. The pillars are not thin columns. In a deep underground salt mine, they are massive, wide enough and tall enough to carry the weight of all the rock above them, which at the depths reached by the Goderich Mine amounts to an enormous vertical load distributed across the pillar grid. The proportions of room to pillar, how wide the rooms can be relative to how much pillar is left, are calculated through geotechnical engineering, a discipline that combines materials science, structural mechanics, and detailed knowledge of the specific rock conditions at each location within the mine. Too wide a room, and the pillar takes more stress than it can safely carry. Too narrow a room, and the efficiency of extraction drops below economic viability. Getting the balance right requires careful measurement, continuous monitoring, and a conservative approach to uncertainty, because the consequences of miscalculation in an underground environment are serious enough that engineers consistently prefer to err on the side of leaving too much rather than too little. The result of this approach, applied consistently across decades of development at the Goderich Mine, is an underground landscape of remarkable visual character. The rooms are large, some of them high enough and wide enough that the human figure standing within them feels genuinely small, absorbed into a space that seems to belong to a different scale of things. The pillars rise from the floor at regular intervals, their surfaces rough with the marks of extraction equipment, their edges occasionally catching light in ways that reveal the internal crystalline texture of the salt. The ceiling, the back, as miners call it, stretches overhead in a broad, slightly irregular plane that gives each room a sense of enclosed but generous space. Walking through the main working areas of the mine feels something like walking through a very large building, but one where the walls, floor, and ceiling are all made of the same pale, faintly luminous material, and where there are no windows, no view of the outside world. No variation in the quality of light except what the artificial lighting of the mine itself provides. The headlamps of individual workers cast pools of white light that move with them as they walk, illuminating a small circle of detail, a section of pillar, a stretch of road surface. The glinting face of a freshly cut salt wall, while the surrounding space recedes into a comfortable dimness. The roads themselves are a significant element of the underground world. They were not an afterthought, but a carefully planned infrastructure system, carved from the salt and maintained as the primary means of moving people and material through the mine. The underground road network follows the general pattern of the room and pillar layout, running through the main extraction corridors and connecting the working areas to the central shaft. Vehicles move through these corridors, specialized underground equipment, primarily diesel or electric powered, that is sized to fit within the tunnel dimensions and designed to operate in the enclosed underground environment. The scale of this equipment, when seen in the context of the underground space, helps calibrate just how large the mine actually is. These are not small vehicles navigating narrow passages. They are substantial machines, moving through corridors wide enough to accommodate them with room to spare, traveling distances that would be impractical on foot. The mine has its own underground logistics system, a network of movement and supply that functions, in miniature, like the transport infrastructure of a small city. Ventilation is another engineering challenge of fundamental importance. Diesel engines and the rock-cutting equipment used in salt mining both consume oxygen and generate exhaust gases, and the underground workforce requires a continuous supply of fresh air that can only be maintained through deliberate engineering. The Goderich Mine's ventilation system moves enormous volumes of air through the underground workings, drawing fresh air down through intake shafts and exhausting contaminated air through separate return airways. The system operates continuously, maintaining air quality throughout the mine to standards that are regularly monitored and carefully maintained. Because the mine extends beneath Lake Huron, because its workings reach outward from the shore and spread beneath the floor of the lake, the ventilation and access shafts that connect the underground world to the surface are of particular engineering significance. These shafts must be carefully sealed and maintained to prevent any possibility of lake water finding a path into the underground workings. The overlying rock provides a substantial natural barrier, hundreds of meters of intact sedimentary formation separating the lake floor from the mine below. But the engineering of the shafts themselves adds an additional layer of deliberate protection. The mine also maintains extensive systems for monitoring the condition of the underground structure. Instruments measure stress on pillars and changes in the dimensions of underground openings. The behavior of the rock is tracked continuously, looking for any indication that conditions are changing in ways that might require engineering response. This is not a passive or occasional activity. It is an ongoing program of observation that reflects the fundamental principle of responsible underground engineering. The underground world must be understood as a living system, one that continues to change slowly over time and must be continuously understood if it is to remain safe. There is an electrical infrastructure to consider as well. The underground world of the Goderich Mine is entirely dependent on electricity for its lighting, for much of its equipment, for its communication systems, and for the operation of the hoisting system that moves personnel and salt between the underground and the surface. Power is delivered through a network of cables and distribution points installed throughout the mine's workings, an invisible nervous system that, alongside the ventilation system, makes sustained human occupation of this underground environment possible. All of this infrastructure, the roads, the ventilation, the electrical systems, the shafts, the monitoring networks, was built incrementally, piece by piece, as the mine expanded over decades. Each addition was designed to serve the immediate need while anticipating future development. The underground world of the Goderich Mine is, in this sense, a record of decisions, of engineering judgments made at different moments across many generations, each one adding something to the structure that subsequent generations inherited and worked within. That inheritance is not merely physical. It is also a form of knowledge about the specific behavior of the salt in this particular location, about the quirks of the underground geometry, about the areas that require more careful monitoring and the areas that have proven consistently stable. This knowledge does not exist entirely in written records or engineering reports, though those are maintained carefully. Much of it exists in the experience of the people who have worked in the mine across its long history, in the accumulated professional judgment of miners and engineers who have spent years learning the particular character of this underground world. That kind of knowledge, embodied, practical, acquired through long familiarity with a specific place, is one of the things that makes any deep underground operation more than simply an engineering project. It is what makes it, in some sense, a community. Not merely a workplace, but a place that people come to know deeply and, in many cases, to feel a quiet and genuine attachment to. The people who built the underground infrastructure of the Goderich Mine were not building an abstract engineering system. They were building a place where they and their colleagues would spend significant portions of their lives, descending in the morning, ascending in the evening, returning day after day to a world that had its own geography, its own landmarks, its own particular quality of silence and light. Understanding the engineering of the mine requires understanding that it was built by people who were simultaneously building their own relationship with it. And that relationship has shaped the mine as surely as any technical specification. The shift change at the Goderich Mine happens at the surface, in the changing rooms and staging areas of the mine's surface complex. It is a practical, unhurried affair, workers arriving for the incoming shift, exchanging brief words with those finishing the outgoing shift, checking equipment, collecting the personal protective gear that underground work requires. Hard hats, steel-toed boots, high-visibility jackets, headlamps, self-rescuers, the personal breathing devices that every underground worker carries and hopes never to need. The ritual of preparation for underground work is deliberate and systematic, each step part of a safety culture that has been built and refined over many generations of underground mining practice. Then the cage descends. The elevator ride to the working level of the mine takes only a few minutes. But it is a transition that experienced miners describe as quietly significant, a daily passage from one world to another that no matter how many times it has been made retains something of its particular character. The light changes, the air changes, the sounds change. Everything above, the weather, the traffic, the visible sky disappears, replaced by the cool, still atmosphere of the underground and the soft white glow of the salt walls. For a miner beginning a shift, the transition is so familiar as to be almost unconscious. They know where they are going. They know the geography of the underground corridors as well as they know the streets of the town above. They know which sections of the mine are currently active, which roads lead to the working faces, which areas require particular attention or care. The underground world has become, through years of daily experience, as legible to them as any landscape, a familiar terrain with its own landmarks and rhythms and quiet particularities. The working day underground has a character shaped by the physical environment in a way that surface work often is not. The temperature underground remains remarkably constant throughout the year, around 10 degrees Celsius in most working areas, cool enough to be comfortable during physical labor, but noticeably different from summer temperatures above ground. The humidity is very low, the dry salt absorbing atmospheric moisture and creating an environment that is noticeably drier than the surface. The air has a faint mineral quality, not unpleasant, but distinctly different from the air above. The absence of natural light is, for many workers, the most significant atmospheric feature of underground work. There is no sunrise visible from the working level, no change in light quality through the day that ordinarily marks the passage of time for people working outdoors. The lighting within the mine, overhead lamps fixed to the ceiling at regular intervals along the main corridors, supplemented by the headlamps that workers wear, is consistent and steady. It illuminates the immediate working environment effectively, but it is artificial light without the warmth or variability of daylight. Workers who spend long shifts underground and then return to the surface often speak of the particular quality of emerging into daylight at the end of a shift, the way the open sky feels after hours spent in the enclosed, evenly lit underground world. The sounds of the mine are layered and particular. In the active working areas, where extraction equipment is operating, there is a steady mechanical noise, the deep percussion of mining equipment cutting through solid salt, the rumble of vehicles moving through the corridors, the industrial rhythms of a working mine. But in the main haulage roads, away from the active faces, the sounds are different. The hum of ventilation fans, the distant echo of machinery, the occasional passage of a vehicle, its engine note changing as it moves through the tunnel geometry. And in the older, quieter sections of the mine, in passages that are no longer actively worked, there can be a silence so complete that it feels almost physical, a presence rather than an absence, as though the underground has a quality of stillness that is genuinely its own. Many miners who have worked in the Goderich Mine for extended periods speak of that silence with a kind of quiet appreciation. It is not an uncomfortable silence. The underground world is not, in their experience, a threatening or oppressive environment. It is simply a very particular one, contained, consistent, removed from the variability and sometimes harsh conditions of surface work. The underground weather never changes. It does not rain underground. It does not snow. The temperature does not drop to -20 in January or climb to 35 in July. For workers who have spent years moving between the underground and the Ontario surface, the reliability of the underground climate has its own modest appeal. The work itself varies depending on a worker's role within the mine's operations. At the working face, the active extraction areas where salt is being cut from the rock, the work is physically demanding and technically skilled. Equipment operators manage large, specialized machines that drill, blast where blasting is used, and load the broken salt for transport. Their work requires a precise understanding of how to operate heavy equipment in confined underground spaces, a skill set that combines mechanical knowledge with spatial awareness in ways that take time to develop and are not easily replaced. Elsewhere in the mine, maintenance crews work to keep the underground infrastructure functional, servicing vehicles, maintaining electrical systems, checking ventilation equipment, monitoring the condition of roads and roofs. Their work requires a different set of skills, but the same underlying familiarity with the underground environment. They know the mine through its systems and mechanisms, through the behavior of its equipment and the particular demands that the salt environment places on mechanical components. Safety culture pervades all of it. Underground mining has a long and difficult history with industrial accidents, and the contemporary mining industry, at least in well-regulated environments like Ontario's, has built an extensive culture of safety awareness and hazard management that shapes every aspect of underground work. Workers are trained to observe and report. They understand that safety in an underground environment depends not only on individual caution, but on the collective attention of everyone working in the same space. The mine's safety record reflects decades of careful management, but the culture that produced that record requires continuous reinforcement. It is not something that can be established once and then forgotten. Among the men and women who have spent careers in the Goderich Mine, a particular perspective tends to develop, one that combines practical expertise with something harder to name. A kind of geological intimacy, perhaps. A familiarity with the underground world that goes beyond knowing where the roads go or which equipment is assigned to which section. The long-term miners of Goderich tend to know their mine in a way that includes an awareness of its geological character, of the places where the salt changes quality, where the roof requires closer attention, where the crystal structure of the rock differs from what is found elsewhere. This knowledge is not always formally articulated. It lives in the hands and eyes and feet of people who have spent years developing it. Consider the generations of families in and around Goderich for whom the mine has been a constant presence across multiple generations. Mining communities tend to develop particular relationships with the underground operations that define their local economy, relationships that are not simply economic but cultural, threaded through the social fabric of the town in ways that shape identity and memory over long periods of time. In Goderich, the mine has been a significant employer for well over a century. The men and women who have worked there across the generations represent an accumulation of human experience within the underground world that is, in its own quiet way, as layered and complex as the geological record in the walls around them. There are stories, not dramatic stories, not the stories of accidents or crises, but ordinary stories of fathers who worked the mine for decades and whose children followed them underground. Of workers who knew every section of the mine's underground geography, as well as they knew their own neighborhoods above ground. Of the particular pride that comes from maintaining expertise in a highly specific and genuinely demanding technical environment. Of being among the people who know how to do something that most of the world has no experience with and no easy way to imagine. These are not exceptional people in any superficial sense. They are, by and large, ordinary people with families and mortgages and interests that have nothing to do with salt or underground geology. But the work they do is genuinely exceptional. It takes place in an extraordinary environment, requires skills that are not easily acquired, and connects them, whether they think about it in these terms or not, to a physical reality that most of humanity never encounters. Every day, they descend into a world that preserves the memory of an ocean that is 400 million years old. And then, at the end of the shift, they ascend again into the ordinary world, bringing with them, perhaps, a particular kind of quiet knowledge about what lies beneath. That daily rhythm, descent, work, ascent, is so habitual for the experienced underground miner that it becomes simply the pattern of working life, as unremarkable in its regularity as any other occupation's daily routine. And yet the place where it is performed remains genuinely remarkable. The walls do not become less ancient because someone has walked past them 1,000 times. The silence of the deeper sections does not become less extraordinary simply because it is familiar. The underground world of the Goderich Mine retains its character regardless of how well it is known, and perhaps that is part of what makes it worth understanding. The engineering that makes human occupation of this underground world possible is, as described in the previous chapter, a careful and continuous effort. But understanding why those engineering structures remain stable, how the mine maintains its extraordinary underground architecture across decades of ongoing extraction, requires a somewhat deeper look at the science of what holds the underground world together. There is a question that almost everyone asks when they first learn about the Goderich Mine. It is not a complicated question. It does not require a geological education or an engineering background. It is simply the most natural thing to wonder when someone tells you that enormous underground rooms have been carved out of solid rock several hundred meters beneath the floor of a great lake. Rooms that have existed for decades, that workers enter and leave every day. That contain roads and vehicles and active machinery. The question is this: what keeps it from collapsing? It is a reasonable thing to ask. The instinct behind it is sound. Remove material from beneath something heavy, and the heavy thing falls. This is basic physics, and the intuition is correct as far as it goes. The surface of the land above the Goderich Mine and the floor of Lake Huron above the portions of the mine that extend beneath the water represents an enormous weight. The rock between the surface and the working level is hundreds of meters thick, composed of layer upon layer of limestone and shale and various other sedimentary formations, each with its own density and its own contribution to the total load pressing downward. That weight does not disappear simply because the material below has been removed. It must go somewhere. It must be carried by something. What carries it, in the Goderich Mine and in Rumand pillar mines generally, is the systematic pattern of salt pillars left in place during extraction. These pillars are not decorative. They are structural, the load-bearing elements of an underground architecture that has been carefully designed to distribute the weight of the overlying rock across the remaining salt in a way that keeps stresses within acceptable limits at every point in the system. The engineering of those pillars begins with an understanding of the mechanical properties of rock salt, how it responds to load, how it deforms under pressure, and under what conditions it fails. Rock salt, as noted earlier, behaves plastically under sufficient stress and temperature. This is actually a useful property from an engineering perspective, because it means that pillars under load will deform gradually rather than failing suddenly. The salt creeps, flowing slowly in response to the pressure placed upon it, in a way that distributes stress more evenly through the pillar cross-section than would occur in a more brittle material. A granite or limestone pillar under the same load might develop stress concentrations at specific points and eventually crack suddenly along those planes. A salt pillar, by contrast, tends to deform slowly and more uniformly, giving engineers time to observe the deformation and respond if necessary. This plastic behavior does not mean that salt pillars never fail. Under sufficient load, or if the pillar dimensions are inadequate for the depth and the properties of the overlying rock, salt pillars can and do reach a point where deformation accelerates beyond recovery. The history of underground salt mining includes examples of pillar failure and the associated ground settlement that follows, though modern geotechnical design, informed by decades of research and operational monitoring, works carefully to prevent such outcomes. At the Goderich Mine, pillar design takes into account several factors that are specific to this particular location and depth. The depth of the working level, several hundred meters below the surface, means that the in situ stress field, the natural state of stress within the rock before any mining takes place, is already substantial. Rock at depth is under pressure from all directions, not just from the weight of the overlying material, but from horizontal stresses generated by the tectonic forces that have acted on the crust across geological time. Understanding this pre-existing stress field and accounting for it in the pillar design is a critical part of ensuring that the underground structure remains stable as mining proceeds. The roof of the mine, the ceiling of each room, the material that spans the space between adjacent pillars, is another engineering consideration of fundamental importance. In the Goderich Mine, the immediate roof above the salt workings consists of the rock formations immediately above the salt layer, generally various shale and limestone units that have their own mechanical properties and their own response to the redistribution of stress that occurs when the salt below them is removed. The behavior of these roof formations is carefully characterized through core sampling, laboratory testing, and ongoing underground observation. In areas where the roof rock is well behaved and competent, large spans can be maintained safely. In areas where the roof requires additional attention, engineering measures are available and applied. What those measures look like in practice varies with the specific conditions. In some cases, the design of the pillar layout is adjusted to provide more support in areas of weaker roof. In others, supplementary support systems, rock bolts installed through the roof rock to stitch together layers that might otherwise separate, are used to reinforce the natural structure. These installations are done proactively, as part of a planned program of ground support rather than as a reactive response to observed instability. The underlying philosophy is conservative. In an underground environment, it is far preferable to provide support that turns out to be unnecessary than to discover that necessary support was not provided. The monitoring program at the Goderich Mine is an ongoing, systematic effort to understand the behavior of the underground structure through time. Instruments embedded in the rock measure stress changes at selected locations. Precision surveys track any movement in the positions of underground reference points. Changes too small to see with the eye, but detectable with the surveying equipment used for this purpose. The condition of roofs and pillars in all active and recently active areas of the mine is regularly inspected by trained personnel who know what to look for and how to interpret what they find. This combination of engineering design, material knowledge, and ongoing monitoring is what allows the underground world of the Goderich Mine to maintain the scale and character that it has. The enormous rooms, the cathedral-like proportions, the sense of generous underground space, these are not accidents of geology alone. They are the product of engineering decisions made with an understanding of the geological conditions and a commitment to working within what those conditions allow safely and sustainably. There is something worth appreciating in the relationship between the mine's engineering and its geology. The two are not in opposition. The engineers who designed and continue to manage the underground structure of the Goderich Mine are not fighting against the geology. They are working with it, using their understanding of how rock salt behaves, how the overlying formations respond to stress changes, and how the entire underground system evolves through time to make informed decisions that keep the mine productive and the underground world intact. The geology sets the terms. The engineering works within them. That working relationship between human engineering and geological reality is one of the defining characteristics of underground mining at its best. It requires genuine knowledge of the underground environment, not just of the rock mechanics, but of the specific quirks and characteristics of the particular formation being worked. And that knowledge, as has been observed already, is built up gradually through observation and experience over many years. The engineering of the Goderich Mine today carries within it the accumulated understanding of all the engineers and geologists who have worked there before, each generation adding to the knowledge base that the next inherits. The underground world they have collectively maintained is, by any reasonable measure, a remarkable engineering achievement. Rooms carved from 400-million-year-old salt, standing stable and accessible beneath hundreds of meters of rock and the floor of a great lake, maintained through a combination of careful design, material understanding, and continuous observation. Not dramatic, not heroic in any conventional sense, but genuinely extraordinary in the quiet, sustained way that the best engineering tends to be. And within those rooms, within the walls and pillars and ceilings of this engineered underground world, there is another kind of knowledge waiting. Not engineering knowledge, and not the knowledge of miners who have learned the character of their workplace, but scientific knowledge encoded in the crystalline structure of the salt itself, preserved across 400 million years, waiting for the right questions to be asked of it. A crystal of rock salt looks simple. It is a small, geometrically regular thing, a cube, if it forms without interference, bounded by flat faces that reflect light in clean, sharp planes. Sodium chloride, arranged by the electromagnetic forces between its ions into a repeating three-dimensional lattice, is one of the most straightforward crystal structures in mineralogy. It has been studied for well over a century, its properties catalogued in exhaustive detail, its behavior under various physical conditions well understood. There is nothing mysterious, on the surface, about a grain of salt, but inside that grain, within the microscopic imperfections, inclusions, and trace constituents that any real crystal inevitably contains, there is information. Information about the conditions under which the crystal formed. Information about the chemistry of the water from which it precipitated. Information about the temperature and concentration and biological environment of the ancient sea in which it crystallized. Information, in other words, about a world that has been gone for 400 million years. This is the fundamental insight that makes evaporite deposits scientifically valuable in ways that extend far beyond their economic importance as mineral resources. The salt in the Goderich Mine and in the broader regional evaporite sequence of which it forms a part is a chemical archive. It is a record, imperfect but partially decipherable, of conditions in a specific part of the ancient ocean during the Devonian period. And reading that record carefully and with the appropriate scientific tools can tell us things about Earth's deep past that are difficult or impossible to determine from any other source. The most immediately accessible form of this information is the chemical composition of the salt itself. The ratio of different ions in the rock reflects the composition of the seawater from which it precipitated. The sequence in which different minerals crystallize out of evaporating seawater is predictable. Calcium sulfate minerals like anhydrite and gypsum tend to precipitate first, followed by halite as concentration increases further, followed by more soluble potassium and magnesium salts if evaporation continues far enough. The presence and relative abundance of these different mineral phases in an evaporite sequence provides information about how far the evaporation cycle proceeded and what the composition of the original brine was. This matters because the composition of seawater has changed over geological time. The ancient ocean was not chemically identical to the modern ocean. The relative proportions of calcium, magnesium, sulfate, and other ions have shifted through geological history in response to changes in volcanic activity, weathering rates, biological productivity, and other large-scale Earth system processes. By analyzing the chemistry of ancient evaporite deposits, geochemists can reconstruct aspects of past ocean chemistry that are otherwise extremely difficult to determine, contributing to a broader understanding of how Earth's ocean atmosphere system has evolved over deep time. Fluid inclusions offer another window into the ancient past. As halite crystals grow, they sometimes trap tiny amounts of the brine from which they are forming microscopic droplets of liquid captured within the crystal's structure as it expands. These inclusions are effectively sealed samples of the ancient brine, preserved within the crystal for hundreds of millions of years. Using specialized analytical techniques, researchers can extract and analyze the chemistry of these ancient fluid inclusions, determining the temperature at which crystallization occurred, the concentration and composition of the brine, and sometimes even aspects of the ancient atmospheric gases that were dissolved in the water. The study of fluid inclusions in Devonian evaporites has contributed to understanding of ancient ocean temperatures and chemistry, providing data points in the broader reconstruction of Devonian climate. The Devonian period is known to have been generally warmer than the present, a greenhouse world with no polar ice sheets and elevated sea levels. But the details of temperature variation through the period and the regional differences in climate conditions are still being worked out. Evaporite deposits, like those at Goderich, contribute specific local data to this larger picture. Microbial life adds yet another layer of scientific interest. Salt is an extreme environment by the standards of most terrestrial life. The high ionic concentrations are toxic to most organisms, and the low water activity within concentrated brines makes cellular function extremely difficult. But a specialized group of microorganisms called halophils, salt-loving organisms, have evolved the biochemical machinery to not only survive but thrive in high salinity environments. These organisms exist in modern salt lakes and evaporating basins, and there is accumulating evidence that halophilic microorganisms were present in ancient evaporite environments as well. Some researchers have reported isolating viable halophilic bacteria from fluid inclusions in ancient salt deposits, organisms that appear to have survived in a state of extreme metabolic dormancy within the trapped brine for geological timescales. These claims are scientifically controversial, as the possibility of contamination from modern microorganisms is always a concern in such studies, and the evidence has been contested in the scientific literature. Current research continues to investigate these findings with improved contamination controls and more sophisticated analytical methods. Whether or not ancient organisms can truly survive within salt inclusions for hundreds of millions of years remains an open and genuinely fascinating scientific question. One that has implications not only for understanding life on Earth, but for thinking about the potential persistence of life in extreme environments elsewhere in the solar system. What is well established, without controversy, is that the organic chemistry preserved within ancient evaporite deposits can provide information about the biological community that was present during the time of formation. Certain organic molecules, biomarkers, as geochemists call them, are produced specifically by particular groups of organisms and can survive in recognizable form within ancient rock for very long periods. Identifying these biomarkers in Devonian evaporite samples provides evidence about which types of organisms were living in and around the ancient sea during its final evaporative phase, contributing to our understanding of Devonian marine biology. The salt also preserves a physical record of geological events that occurred while the evaporite sequence was being deposited. Changes in crystal texture, the size, shape, and orientation of halite crystals within different layers record changes in depositional conditions. Layers of shale or fine-grained carbonate material intercalated within the salt record episodes when the evaporative conditions were interrupted by influxes of normal marine sediment. Dissolution surfaces, boundaries, where the top of an older salt layer was partially dissolved before new material was deposited above it. Record periods of renewed flooding when less concentrated water entered the basin. Reading these physical textures requires experience and care, but they tell a sequential story, a narrative of changing conditions in the ancient basin, of cycles of evaporation and flooding and evaporation again, of a sea in the process of disappearing over a period of many millions of years. That story is written in the walls of the Goderich Mine in a language that requires geological training to read, but whose fundamental character, a record of slow change across deep time, is comprehensible to anyone willing to attend to it. The industrial and commercial uses of salt produced by the Goderich Mine connect this ancient geological story to the ordinary rhythms of modern life, in ways that are easy to overlook, but worth acknowledging. The salt produced here is used primarily for road de-icing, the application of rock salt to winter roads to prevent the formation of dangerous ice, a practice that consumes enormous quantities of salt across the Great Lakes region and throughout the northeastern part of North America each winter. Salt from the Goderich Mine is loaded onto ships in the harbor below the mine's surface facilities and distributed across a wide geographic area, eventually being spread on roads and sidewalks and parking lots, where it dissolves into the water and runoff of a northern winter and disperses back into the broader environment. There is a somewhat poetic quality to this cycle, ancient ocean salt, which traveled from a tropical Devonian sea into solid rock across 400 million years, being returned to the surface and eventually, in diluted form, back into the water cycle. The salt does not disappear when it is applied to a winter road. It dissolves, it flows with the meltwater into drainage ditches and streams, and eventually into the groundwater and surface water systems of the region. The environmental implications of this dispersal have become a subject of increasing scientific attention, as accumulated road salt has measurably increased the salinity of freshwater bodies throughout the Great Lakes watershed, an unintended consequence of the large-scale use of an ancient geological resource. This environmental dimension of salt mining and use represents a genuine complexity, one that the industry, regulators, and researchers are working to understand and manage. It does not diminish the value of the mine or the legitimacy of its operations, but it does add another layer to the story of the Goderich Salt deposit, a layer in which the ancient geological material intersects with modern ecological realities in ways that require ongoing attention and careful management. The science contained within the walls of the Goderich Mine is, in this sense, not only a matter of historical geology, it is also a matter of contemporary environmental relevance. The deposit is simultaneously an archive of Earth's past and a resource whose extraction and use has consequences for the present. Both of those dimensions deserve to be understood and held together. The deep geological time of the formation on one hand, and the immediate ecological context of its current use on the other. There is much that remains to be learned from the evaporite deposits of the Great Lakes region. The analytical techniques available to geochemists and paleoclimatologists continue to improve, allowing the extraction of increasingly fine-grained information from ancient mineral samples. Each improvement in analytical capability opens new questions about the Devonian Sea, about its temperature, its chemistry, its biology, and its relationship to the broader global climate system of 400 million years ago. The walls of the Goderich Mine, in this sense, are not simply a record of the past. They are an ongoing scientific resource, a place where questions about Earth's deep history can still be asked, and with sufficient patience and the right tools, answered. Yet for all the science that can be extracted from the salt, all the paleoclimate data and geochemical signatures and fluid inclusion chemistry, the most immediate and human dimension of the Goderich Mine has always been simpler than any of that. It has been about the community that grew up around the resource, the town above the mine, the families whose livelihoods have been connected to the underground world across multiple generations. The particular character of a place shaped by its geology in ways that most people never think about and rarely see. Goderich did not become a salt town by accident. The relationship between the town and its underground geology was not something that was planned or designed. It emerged gradually as the scale of the deposit beneath the community became clear, and as the economic possibilities that deposit offered were developed over many decades. But once established, that relationship shaped the town in ways that run deeper than employment statistics or industrial output. Ways that have to do with identity, with community memory, with the particular texture of life in a place whose most significant feature is invisible to the eye. From the harbor, which has served as the working interface between the mine and the wider world, since commercial salt production began in earnest in the 19th century, the lake stretches westward toward the American shore. Its color changing through the seasons, from the deep blue of summer to the gray-green of autumn to the pale ice-edged pallor of winter. Ships have been loading salt in this harbor for well over a century, vessels that have grown larger and more specialized across that period, but that have maintained the same fundamental function, taking the product of the underground and distributing it across the Great Lakes and beyond. The harbor is one of the points where the underground world becomes visible at the surface. Salt moving from the mine through the processing and loading facilities at the lake shore is the tangible product of everything that happens below. The extraction, the crushing, the sizing, the transport through underground roads to the shaft, the hoisting to the surface. Watching a ship being loaded in the Goderich harbor is, in a sense, watching the end of a process that began several hundred meters underground in rooms carved from a 400-million-year-old sea. The town's connection to salt extends into its local culture and identity in ways that are not always immediately obvious to visitors. Goderich has been called, with some promotional enthusiasm, the prettiest town in Canada, a description that refers to its attractive town square, its well-maintained Victorian architecture, and its position above the lake, with views that change dramatically through the seasons. The town takes genuine pride in its appearance and its history, maintaining a local museum and heritage sites that document the development of the community from its earliest settlement through its industrial growth. The salt mine is part of that history, a presence acknowledged and in some ways celebrated in the town's self-understanding. Generations of Goderich families have had members who worked in the mine at some point, and the particular experience of underground work, the daily descent, the underground geography. The distinctive qualities of the workplace below has contributed a thread to the local memory that distinguishes Goderich from towns without this underground dimension. The economic relationship between the mine and the town has been direct and sustained across a long period. The mine has been one of the major employers in Huron County for well over a century, providing wages and benefits that have supported families and, in turn, local businesses, schools, and community institutions. The fluctuations in the mining industry, periods of strong demand and periods of reduced production, have been felt in the community as they are in any resource-dependent town. The local economy has diversified over time, with tourism, agriculture, and various service industries contributing alongside the mine. But the mine has remained a steady and significant presence in the economic life of the region throughout. The seasonal rhythm of salt demand adds a particular character to the mine's relationship with the town and the broader region. Road salt is most heavily demanded during winter, when ice and snow create dangerous driving conditions across the Great Lakes states and provinces. This seasonal demand means that the mine's production schedule is influenced by factors far removed from its underground geography, by the weather forecast, by snowfall patterns across a broad region, by the inventory levels of road authorities in Ohio and Michigan and Ontario, who depend on reliable salt supplies to keep their roads passable through the winter months. In years with severe winters, demand can strain supply, and the mine and its storage and distribution systems operate at high capacity. In milder years, the relationship between production and demand is more relaxed. This connection to the weather, to conditions above ground and often hundreds of kilometers away, is one of the ways in which the underground world of the Goderich Mine is not actually isolated from the surface world, but deeply connected to it. Embedded in economic and social systems that extend far beyond the boundaries of the mine itself. The environmental management of the mine's operations has also become an increasingly significant aspect of its relationship with the surrounding community and the broader region. The lake that sits above portions of the mine's workings is not merely a geological feature. It is a living ecosystem, a source of drinking water for communities along its shores, a habitat for fish and waterfowl, and a landscape of considerable cultural and recreational significance. The mine's obligation to protect Lake Huron from any impact of its underground operations is legally mandated and operationally fundamental. The engineering standards applied to shaft construction and underground infrastructure reflect this obligation. And the monitoring systems in place continuously verify that the mine's workings are not affecting the quality or quantity of water in the lake above. The relationship between the mine and the lake is one of the most distinctive aspects of the Goderich operation, and one that requires continuous engineering and environmental vigilance. That the mine has operated for as long as it has, at the scale it has, without any significant environmental incident involving the lake, reflects the care with which the underground engineering has been managed across many decades. It also reflects an understanding, embedded in the mine's operational culture, that the lake is not simply a geological feature overhead, but a responsibility, a shared resource whose integrity must be protected as a matter of obligation to the communities and ecosystems that depend on it. That sense of responsibility to the lake, to the community above, to future generations who will inherit both the mined-out underground and the surface world, is part of what gives the Goderich Mine a character that extends beyond its industrial function. It is a working mine, a productive industrial operation generating a commercially valuable commodity. But it is also a place embedded in the natural and social landscape of the Great Lakes region in ways that require it to be understood in a much broader context. The families of Goderich who have lived alongside the mine across multiple generations carry that broader understanding as part of their local inheritance. They know, in the way that proximity across time creates knowledge, that the mine is a complex thing, economically significant, geologically extraordinary, operationally demanding, and environmentally consequential all at once. They live with the presence of the underground world in a way that most people never do, and that long familiarity has shaped their relationship to the place in ways that are not easily summarized, but are unmistakably real. In the evenings, when the shift changes and the miners ascending in the cage step out into whatever weather the Ontario sky is offering that day, the transition from the underground world back to the surface world happens quickly, but not without its own quiet moment. The cool, dry air of the mine gives way to whatever the surface is doing: rain, wind, sunshine, snow. The constant temperature of the underground world gives way to the variable reality of the seasons. The artificial light of the mine gives way to natural light, which, depending on the time of year and the time of day, might be the flat grey of a winter afternoon or the long gold of a summer evening over Lake Huron. In those moments of transition, the underground world retreats back below the surface, back into the geological depths, back into its own quiet and particular reality. The mine continues without those who have just left it. The ventilation keeps circulating. The monitoring instruments keep recording. The salt walls stand in the same steady silence they have maintained for 400 million years, indifferent to the shift changes and the seasons and the weather above them, holding their ancient crystalline memory in the cool and the dark. And there are parts of that underground world that the miners of the active sections rarely visit. Older tunnels, abandoned as extraction moved elsewhere. Passages that run into the increasing darkness of unexplored or seldom visited ground. Areas that the current mine mapping shows, but that see few human footsteps in the course of an ordinary working year. These quieter corners of the underground world hold their own particular interest, places where the evidence of older work is preserved alongside the unmodified salt of the original formation, where the layers of human and geological history sit side by side in a silence that feels, even to experienced underground workers, somehow different from the silence of the active mine. It is to these quieter places that the next part of this journey now turns. There are parts of the Goderich Mine that see almost no human presence across the course of an ordinary working year. Not because they are inaccessible. The underground road network connects most areas of the mine to the main shaft without requiring any unusual effort to reach. Not because they are unsafe. The engineering standards applied throughout the mine do not permit areas that fall below acceptable stability thresholds to remain open, but simply because extraction has moved elsewhere, because the working faces have advanced to newer ground, because the particular corners of the underground world that were once the active frontier of the mine's development have been left behind as that frontier moved outward. In these older sections, something happens that is difficult to describe precisely, but unmistakable to experience. The sounds of the active mine, the machinery, the vehicles, the industrial rhythms of a working operation fade with distance until they become barely detectable, a faint suggestion of mechanical activity somewhere far away. The air remains clean and still, the ventilation system maintaining its continuous circulation even through areas that are no longer actively worked. The temperature is the same as everywhere else underground, that steady, cool, unwavering 10 degrees that the salt environment maintains regardless of season or time of day. But the quality of the silence is different. In the active sections of the mine, silence is always partial, always punctuated by the sounds of work, by the movement of people and equipment, by the ordinary noise of an operating industrial facility. In the older, quieter sections, silence becomes something closer to complete. A headlamp illuminates a stretch of corridor that looks much as it did when it was last actively worked. The pillar surfaces carrying the marks of extraction equipment, the road surface worn smooth by decades of vehicle passage. The ceiling overhead in its long, unbroken plane, but the corridor is empty and the sounds that once filled it are gone, absorbed somewhere into the enormous geological fact of the surrounding salt. Walking through these areas is a genuinely unusual experience. The scale of the underground world becomes perhaps more apparent here than in the active sections, precisely because there is nothing else to attend to. No machinery to step around, no vehicles to yield to, no colleagues moving through the same space. Only the white walls, the white ceiling, the pale floor, and the absolute absence of everything that exists above ground. The sky, the wind, the horizon, the variable and restless world of the surface. These older sections are also the places where the physical evidence of the mine's long history is most concentrated. Earlier generations of mining equipment left their marks on pillar surfaces and tunnel walls in patterns different from those produced by modern machinery. The geometry of the older rooms reflects the engineering understanding and the equipment capabilities of the era in which they were created, often somewhat different in proportion and layout from the rooms created by current methods. Reading these differences in the underground landscape requires knowledge, but the broad outlines of a changing technology and a developing understanding of the underground environment are visible even without specialized expertise. In some areas, the infrastructure of earlier periods, wooden beams used for temporary support, steel rails from an era when ore cars were used rather than modern haulage vehicles, electrical fittings of an older design, survives in quiet preservation within the salt. The low humidity of the underground environment, which prevents the kind of deterioration that would rapidly claim these materials at the surface, allows them to persist in a state of arrested decay, neither well preserved nor entirely gone. They occupy the underground world as artifacts of its human history, physical evidence of the generations of people who worked here before the current workforce inherited the mine. The scientific potential of these older areas extends beyond their historical and atmospheric character. Underground spaces that have been stable for decades provide opportunities for geological observation that are not available in active working areas, where the cycle of extraction and the movement of equipment disturb the rock environment continuously. In the older sections, the salt has had time to equilibrate to its current stress conditions, to complete whatever slow deformation the removal of the surrounding material initiated, and to settle into a stable configuration that can be studied and characterized without the complicating factor of ongoing disturbance. Geological mapping in these areas, the systematic documentation of rock types, structural features, changes in salt quality, and the geometry of the layering within the evaporite sequence, contributes to the overall understanding of the deposit. Every observation made underground adds to the three-dimensional model of the salt formation that guides current and future mining decisions. The older sections of the mine, in this sense, are not simply historical remnants. They are a continuing scientific resource, available for observation and study in ways that the actively worked areas are not. Modern technology has added new dimensions to the documentation of underground spaces. Laser scanning, the use of instruments that emit rapid pulses of laser light and measure the return time and direction of each pulse to build a detailed three-dimensional point cloud of the surrounding space, has been applied in underground mining environments to create highly accurate geometric records of tunnel shapes, room dimensions, and pillar profiles. These digital records can be compared against earlier surveys to detect any changes in underground geometry over time, providing a sensitive tool for monitoring the long-term stability of the underground structure. Digital mapping of the full extent of the Goderich Mine's underground workings is an ongoing effort, one that will produce, when complete, a three-dimensional representation of the underground world that can be navigated, virtually measured precisely, and compared against future surveys to track any changes in the structure across time. This digital underground has a particular scientific value in that it captures the current state of the mine at a level of detail that no previous technology could have achieved, creating a record that will remain useful long after the specific conditions it documents have changed. There are also areas of the mine's immediate geological neighborhood that remain, in a meaningful sense, unexplored. The salt deposit extends beneath Lake Huron in directions and to extents that are known in general outline from surface drilling and geophysical surveys, but have not been confirmed through underground observation. The current mine workings represent one portion of a geological formation that reaches considerably farther, both laterally, extending under more of the lake floor, and vertically, with salt-bearing horizons at different depths within the stratigraphic sequence. The question of how far the deposit extends, of what lies beyond the current boundaries of the underground workings, in the geological darkness beneath the deeper portions of Lake Huron, is one of the genuinely open questions associated with the Goderich Formation. It is a question that is being addressed through ongoing geological investigation, through the analysis of geophysical data acquired from the lake surface, and through the integration of existing underground observations with surface and subsurface geological mapping. The answers that emerge from this investigation will shape future decisions about the mine's development, about where and how deeply extraction might eventually proceed. But beyond the purely economic and engineering dimensions of this question, there is a simpler curiosity at its heart. The underground world of the Goderich Mine, for all its extent and complexity, is still only a portion of the underground landscape that exists beneath Lake Huron. The lake sits over a geological structure that is, at depth, far more complex and extensive than the visible surface of the water would ever suggest. Beneath that still, familiar surface, beneath the reflections of cloud and sky that make Lake Huron look so perfectly ordinary from the shore, there is a subsurface world of geological formations extending to depths far greater than any mine has ever reached. Carrying records of Earth's history across timescales that dwarf even the 400 million years of the Goderich Salt. That deeper underground, the geological world, that no mine and no drilling program has yet fully characterized, represents one of the genuinely unknown frontiers of the Great Lakes region. Not unknown in the dramatic sense of unexplored wilderness, but unknown in the quieter and perhaps more profound sense of a natural system that has not yet been fully described, whose complete character and history are still being pieced together from fragmentary evidence. It is the kind of unknown that science approaches not with urgency or drama, but with patient, systematic inquiry, one observation at a time, one sample at a time, one well-characterized question at a time. The Goderich Mine sits at the edge of that larger unknown, serving simultaneously as a window into the underground world and as a reminder of how much of that world remains beyond the reach of human observation. The tunnels end. The lights stop. The mapped and managed underground world gives way, at its boundaries, to geological space that has never been entered by a human being and may never be. That boundary between the known underground and the unknown geological depths is not marked by any sign or barrier. It is simply where the mine's workings stop and the unmodified rock continues, and in the quiet of the older sections, where the sounds of active work have long since faded, that boundary does not feel far away. It is there, somewhere in the darkness beyond the reach of the headlamp, where the white salt walls extend without interruption into ground that no human project has yet required anyone to enter. The mine's future, its continuation, its eventual completion, and the long question of what comes after is the final dimension of this underground story that deserves quiet consideration. Every mine eventually ends, not always dramatically. Not necessarily with the sudden exhaustion of the deposit or the abrupt closure of the facility. Often, the ending of a mine is a gradual process, a long transition through declining production, changing economics, evolving technology, and the slow accumulation of decisions that eventually resolve into the recognition that a particular chapter of a particular place's history has reached its conclusion. The Goderich Mine has not reached that point. It is an active, productive operation, and the salt deposit it works is large enough to sustain continued mining for a considerable period into the future. The questions about what comes after the mine's productive life are not immediately pressing in any operational sense, but they are worth thinking about, worth raising quietly. In the reflective context of a documentary that has spent considerable time exploring the geological and human history of this underground world. Because the way we think about the future of places like the Goderich Mine reveals something about how we understand the relationship between industrial activity and the natural and cultural heritage that industrial activity inevitably touches and, in some cases, creates. The underground world of the Goderich Mine is in a meaningful sense a form of heritage, even though it was created as an industrial facility rather than as a heritage site, even though its primary purpose has always been economic rather than cultural. Even though most of the people who built it and work in it have never thought of it in heritage terms at all. It is heritage because it is a record of geological time, of human engineering, of community history, of the particular relationship between this town and this underground deposit across more than a century of working connection. When mining eventually ends in any section of the underground, whether because the accessible salt has been exhausted there, or because geological or engineering conditions make continued working impractical, or simply because the economic calculus of mining in that area no longer justifies the investment, what remains is a permanent feature of the underground landscape. The rooms and pillars and corridors do not disappear when the mining is done. They continue to exist in geological time for as long as the overlying rock remains stable and the underground structure maintains its integrity. The evidence of human work, the tool marks on the pillar surfaces, the road patterns in the floor, the remnant infrastructure of earlier periods, persists within the salt alongside the geological record that was there long before any human being descended into the ground. This persistence raises a question about how such places should be understood and potentially managed. Underground mining environments that have been worked out, that have completed their productive lives, have been used for a variety of purposes in different parts of the world. Some have been repurposed as underground storage facilities, taking advantage of the stable, constant temperature environment for the preservation of documents, food, or other materials sensitive to temperature and humidity fluctuations. Some have been developed as tourist attractions, their underground landscapes made accessible to the public through guided tour and interpretive programs. Some have been proposed as sites for scientific facilities that benefit from the shielding provided by the overlying rock, physics experiments requiring low radiation backgrounds, for instance, or long-term environmental monitoring stations. The salt mines of Europe have provided instructive examples of various approaches to underground heritage. The Goderich Salt Mine in Poland, one of the most famous underground heritage sites in the world, and now a UNESCO World Heritage Site, was continuously mined from the 13th century until 2007, when salt production finally ended after 700 years of operation. During its long productive life, miners at Goderich carved elaborate sculptures and chambers from the salt, including a remarkable underground chapel with salt chandeliers and salt-carved figures that now draws hundreds of thousands of visitors each year. The transition from working mine to heritage attraction was gradual. Tourism at Wieliczka began while the mine was still operating, and the cultural and historical significance of the underground world was recognized and developed alongside the continuing industrial activity. The circumstances at Goderich are different in significant ways. The mine is younger than Wieliczka, its underground world less elaborately decorated, its heritage dimensions less formally recognized, but the parallels are nonetheless suggestive. The Goderich Mine's underground landscape has its own distinctive character, geological rather than artistic in its origins, but no less striking for that. The pale, crystalline corridors, the enormous pillar-supported rooms, the cool and still atmosphere, the absolute quiet of the older sections. These are qualities that have genuine appeal to people who have the opportunity to experience them. And that represents something worth thinking carefully about as the mine's long-term future continues to unfold. The technology of underground mining has changed significantly across the history of the Goderich operation and continues to change. Modern mining equipment is more efficient, more precise, and more instrumented than the equipment of earlier generations, capable of extracting salt at rates and with a degree of planning accuracy that would have been impossible in the earlier decades of the mine's history. Environmental monitoring systems have become more sophisticated, providing more detailed and more continuous information about the condition of the underground structure and its relationship to the surface and lake environments above. Communication systems allow underground workers to remain in contact with the surface at all times, a significant improvement in safety management compared to the conditions under which earlier generations of miners worked. These technological changes have transformed the experience of underground work in ways that are both obvious and subtle. The heavy manual labor that characterized earlier generations of mining has been largely replaced by the operation of mechanized equipment, a change that has improved safety and productivity while altering the physical character of underground work in ways that experienced miners sometimes reflect on with a certain ambivalence. The direct physical engagement with the rock, the intimate knowledge of the material that came from working close to it, is harder to maintain when the primary interface is the controls of a large machine rather than hand tools and immediate physical contact with the salt face. The transmission of knowledge between generations of underground workers is itself a heritage dimension that deserves acknowledgement. The accumulated expertise of experienced miners, the knowledge of how the rock behaves, of what sounds and visual cues in the underground environment mean, of how to read the condition of a roof or a pillar in ways that formal measurement alone cannot fully capture, is not easily codified in training manuals or engineering reports. It lives in the experienced judgment of people who have spent years developing it, and it passes between generations through direct professional contact, through mentorship and observation, through the shared experience of working in the same underground environment over time. As the workforce of any mine changes across generations, as experienced workers retire and new workers enter, there is always a question of how effectively that accumulated knowledge can be transmitted. Modern training programs and documentation practices address this challenge as systematically as possible. But the kind of knowledge that comes from long familiarity with a specific underground environment has a quality that resists complete formalization. It is, in part, embodied knowledge, knowledge that lives in the body and the perception as much as in the mind. Maintaining that kind of knowledge across generational transitions is one of the quieter challenges of any long-lived underground operation. Environmental stewardship is another dimension of the mine's future that deserves sustained attention. The question of how the production and use of road salt affects the freshwater ecosystems of the Great Lakes region, including the lake that sits directly above portions of the mine's workings, is one that science, industry, and regulatory bodies are working to understand more fully. Research into alternatives to chloride-based de-icing materials, into more efficient application methods that reduce the quantity of salt required, and into the ecological effects of elevated salinity in freshwater systems is ongoing and gradually advancing. The mining industry is not the only stakeholder in this conversation. Road authorities, municipal governments, environmental agencies, and the scientific community all have roles to play in working toward more sustainable winter road management practices. For the mine itself, environmental responsibility takes the form of careful management of its operational impacts on the surrounding geological and hydrological environment, ensuring that its underground workings do not affect the integrity of the lake above, that its surface operations manage drainage and runoff responsibly, that its overall footprint on the natural systems of the Huron County area is understood, monitored, and kept within acceptable limits. This is not a simple or static obligation. The standards of environmental management continue to evolve as scientific understanding of the relevant systems improves and as societal expectations of industrial facilities become more demanding. The mine's future will be shaped in part by how effectively it adapts to those evolving standards. All of these considerations, the question of underground heritage, the evolution of mining technology, the transmission of specialized knowledge, the environmental responsibilities of a major industrial operation, converge in the question of what the Goderich Mine will eventually become when its productive working life is finally complete. That question has no immediate answer. The mine continues. The salt continues to be extracted, processed, shipped, and spread on winter roads across a broad region. The underground world continues to expand slowly as the working faces advance through the ancient deposit. But the question is worth holding quietly as a background awareness, a recognition that this extraordinary underground world is, in the largest sense, temporary. Not temporary in any human timeframe, the underground landscape created by more than a century of mining will persist for a very long time after the last shift ascends, but temporary in the context of the geological time that produced the deposit in the first place. The mine is a moment in the history of the salt, a long moment by human standards, but a brief one by the reckoning of deep geological time. The salt was here for 400 million years before the first miner descended into it. Whatever becomes of the mine in the future, the geological reality that produced the underground world, the ancient sea, the long evaporation, the burial and preservation across inconceivable stretches of time, will remain as the fundamental fact of the place. And that fact, perhaps, is the most appropriate note on which to begin the final passage of this underground journey. There is a particular quality to the silence of an underground salt mine that is unlike any other silence. It is not the silence of a quiet room, which is always permeable, always admitting the faint sounds of the world outside, traffic through a closed window, birdsong from a distant garden, the almost subliminal vibration of a building that contains living people going about their ordinary business. It is not the silence of an empty field or a still morning on the lake shore, which is a natural silence, rich with the potential for sound, filled with the soft movement of air and the subtle sounds of things growing and living. The silence of the Goderich Mine's deeper and quieter sections is a different thing. It is the silence of something sealed, of a world that has been closed away from the surface for 400 million years and carries, in its atmosphere, the character of that long isolation. The sounds of the surface world simply do not exist here. They cannot reach this depth. They are absorbed by the hundreds of meters of solid rock that separate the underground from the sky, and what remains in their absence is a quiet so complete that it has a presence of its own, as though the absence of sound were itself a substance, something with weight and texture that the ear recognizes and the body understands. For people who have spent time in this underground quiet, miners at the end of a long shift, geologists completing their observations in a remote section of the mine, engineers checking the condition of an older corridor, the silence does not feel empty. It feels full. Full of the geological time that has accumulated here, of the weight of the rock overhead and the lake above that, of the extraordinary fact of being in a place that was built not by human design, but by the patient workings of planetary processes across timescales that the mind cannot comfortably inhabit, but can at least genuinely reach toward. It is worth returning, in this final passage, to the beginning, to the surface of Lake Huron, to the particular quality of the light on the water on a calm afternoon in late autumn, to the way the lake seems to hold the sky in its surface, and the horizon seems impossibly distant when the water is still. The lake is beautiful in the way that large freshwater bodies can be, an inland beauty different from the salt ocean, quieter in scale but no less genuine in its effect on the person standing at the shore and looking out. From that shore, nothing about the lake suggests what lies beneath it. The water is opaque. It reveals nothing of its floor, let alone of the geological formations that lie beneath that floor, let alone of the ancient evaporite sequence that rests within those formations, let alone of the mine that human hands have carved into that evaporite sequence over the past century and more. The surface of the lake is a perfect concealment, as ordinary and as beautiful as a lake surface should be, giving no indication of the extraordinary hidden landscape that it covers. This concealment is not intentional, of course. The lake does not hide the mine. The geology does not withhold itself as a matter of preference. The underground world is invisible from the surface simply because That is the nature of underground worlds. They require descent to be known, and descent requires both the physical means to go down and the curiosity to want to. Most people who have ever stood on the shore of Lake Huron and looked out over the water have had neither the means nor the reason to descend into what lies beneath, and so the underground world has remained for most of its human history. A place known only to those whose work or study has taken them there. This documentary has tried, in some small way, to make that descent without requiring the elevator. To carry the viewer gently downward through 500 meters of rock and geological time, into a world of white salt corridors and ancient crystal walls, and the particular cool stillness of an underground environment that has been accumulating its character for longer than the mind can easily hold. To make the Goderich Mine legible, not as an industrial facility, not as an economic resource, not as an engineering system, though it is all of those things, but as a place. A place with a history and a character and a quality of presence that deserve to be known and quietly appreciated. The geological history of this place is, at its deepest level, a story about time. About what happens when time is given sufficient latitude to work with the simple materials of sea water and sunlight and pressure and burial. The result, in this case, is 400 meters of crystallized ocean, an ancient sea made solid, preserved beneath a younger lake, waiting in the cool and the dark with the patience that only geological features can maintain. There is no urgency in that waiting. There is no impatience, no awareness, no anticipation. The salt simply is as it has been continuously for 400 million years. It is one of the oldest materials that a human hand is likely to touch in the ordinary course of life, and that fact alone is worth a moment of quiet appreciation. The human history of this place is a story about a different kind of patience, the accumulated patience of generations of working people who have given their professional lives to the task of understanding and extracting this ancient geological resource. The miners of Goderich have not, for the most part, descended into the ground as adventurers or explorers. They have gone down as workers, doing skilled and physically demanding work in an unusual environment, bringing with them the practical expertise and the professional culture that their predecessors left them and passing it forward to those who came after. Their relationship to the underground world is not romantic, but it is real, the relationship of people who have spent enough time in a specific place to know it in the particular, detailed, embodied way that long familiarity produces. That kind of knowing, not the knowing of the geologist who studies the salt's chemistry or the engineer who designs its extraction or the documentary narrator who tries to translate its character into words, but the direct habitual knowing of people who work there every day, who know which corridor echoes differently from its neighbors, who can navigate the underground road network without thinking, who carry the geography of the mine in their bodies as well as their minds, is a form of knowledge that deserves its own quiet recognition. It is the knowledge of people who have made an extraordinary place ordinary through the simple act of showing up to it, day after day, for a working lifetime. There are miners who have spent 30 years or more descending into the Goderich Mine, who have watched the underground world expand around them as new sections were opened, and watched older sections grow quiet as extraction moved on. They have watched the technology change. They have watched colleagues retire and new workers arrive. They have experienced the underground in all the ordinary moods of a working day, in the focused concentration of a technically demanding task, in the quiet routine of maintenance work, in the particular fellowship of people sharing an unusual environment, in the simple physical satisfaction of a shift completed and the elevator rising again toward the surface. When those workers emerge at the end of a shift into whatever the Ontario sky is offering, the long summer light of an evening that will not quite darken, or the deep winter dark of a late afternoon that has already given up on daylight, they carry with them something that is not entirely separable from the underground world they have just left. Not literally, not in any mystical sense, but in the practical sense that long familiarity with any remarkable place leaves a residue in the person who has experienced it, a quiet background awareness of what the place is, what it contains, what it represents. The geological time of the Goderich Mine does not diminish in its significance because a miner has walked past the ancient salt walls 1,000 times. The 400 million years that the walls represent do not become less extraordinary simply because they are familiar. The underground world retains its character, its whiteness, its coolness, its extraordinary stillness, its quality of preserved geological memory, regardless of whether anyone is present to notice it. The mine continues whether it is attended to or not, maintaining its underground existence in the cool and the dark beneath the lake, as it has maintained it for every moment of the more than a century since human beings first broke through into the solid salt and began carefully and incrementally to make it known. The lake continues too, above and indifferent, its surface responding to wind and temperature and the slow seasonal rhythms of a great lake that has existed in its current form for only a geological moment, compared to what lies beneath it. The water moves. The light changes on it through the day and through the year. Fishing boats cross it in summer, and in severe winters, ice forms along its shallow margins and sometimes spreads across its surface in a white sheet that briefly makes the lake look like something solid. But beneath that surface, beneath the water column and the lake sediment and the layered sedimentary rock and the hundreds of meters of geological formation that separate the surface world from the underground, the salt remains exactly as it is, cool, still, white in the light of any lamp directed at it, and perfectly dark in the absence of that light, ancient beyond any ordinary measure of age, quiet beyond any ordinary measure of quiet. The corridors stretch on in the darkness beyond the last working light. The pillars stand in their measured rows, carrying the weight of everything above them with the slow, plastic patience of a material that does not know how to resist, but only how to yield gradually, without breaking, across time. The crystal walls hold their inclusions of ancient brine, those microscopic sealed samples of a sea that has not existed for 400 million years, with the same indifference to time that characterizes everything geological. The ventilation moves the air through the tunnels in a slow, steady circulation that the mine requires, and the mine maintains, as it has maintained it through every shift and every season and every year of its long working life. And somewhere in the older sections, in the quiet corridors where the sounds of the active mine have long since faded to nothing, where the road surface is worn smooth by decades of vehicles that no longer travel it, where the salt walls are unchanged from the day the last equipment moved through, there is a silence that is almost geological in its depth. A silence that belongs as much to the 400 million years behind it as to the present moment. A silence that is not empty, but full of time, full of patience, full of the quiet geological fact of an ancient sea made solid and preserved beneath a younger lake, waiting with the enormous unhurried equanimity of deep geological time for whatever comes next. Above, the waters of Lake Huron continue their quiet rhythm beneath the changing sky. Beneath, the white corridors remain just as they have for all the time that human beings have known about them, and just as they were for incomprehensibly longer before that knowledge existed. The salt remembers. The silence remains, and beneath the waters of Lake Huron, Earth's hidden cathedral continues waiting, patient and still and ancient, in the quiet darkness below.